What if we're not alone? For centuries, humans have gazed at the stars, wondering if other worlds might harbor life. And now, we stand on the brink of answering that ancient question. Out there, hidden in the vast darkness between the stars, worlds unlike anything in our solar system orbit distant suns. Some are scorching hellscapes, others frozen wastelands, but a rare few glow with possibility. These are the exoplanets, alien worlds circling far-off stars, and among them lie the most tantalizing discoveries of our time, planets that could just maybe host life beyond Earth. Right now, astronomers are peering into the atmospheres of these distant orbs, hunting for the faintest chemical whispers of biology. Imagine standing on the surface of one of these worlds beneath an unfamiliar sun, where the very air might thrum with the presence of something extraordinary. The search for these cosmic oases has transformed from science fiction into hard science, thanks to breakthroughs that let us detect planets hundreds of light years away. These aren't just dots on a telescope's read out their entire worlds with their own climates, geographies, and perhaps even biospheres. Some orbit in the Goldilocks zone, that perfect distance from their star where water could pool into lakes, rivers, even oceans. Others defy our expectations entirely, with conditions that challenge everything we thought we knew about where life can thrive. The more we find, the clearer it becomes. Earth might not be the exception in the universe. It might be one of many homes to life, scattered like islands in an endless cosmic sea. This journey into the unknown is what makes exoplanet science so electrifying. Every new discovery peels back another layer of mystery, bringing us closer to the ultimate revelation. Are we truly alone? Today, we're diving into 30 of the most promising exoplanets ever found, worlds where the ingredients for life might already be mixing. From boiling super-Earths to hidden water worlds, each holds clues written in light and chemistry, waiting to be decoded. Some could host microbes, others, civilizations advanced beyond our wildest dreams. So let's set sail across the cosmic ocean, because out there, in the quiet dark, the universe might be whispering back. Just 4.2 light-years away, practically next door in cosmic terms, lies a world that could rewrite the story of life in the universe. Proxima Centauri b orbits the closest star to our Sun, a dim red dwarf called Proxima Centauri, and it's the most tantalizing nearby candidate for habitability we've ever found. Picture a planet roughly 1.3 times the mass of Earth, likely rocky, with just enough warmth to allow liquid water to exist on its surface. That's the dream, at least, but here's where things get complicated. Proxima Centauri isn't a gentle star like our Sun. It's a tempestuous red dwarf prone to violent flares that blast out torrents of radiation. These stellar eruptions could strip away atmospheres and bathe the planet's surface in deadly ultraviolet rays, turning what might have been a paradise into a scorched wasteland. Yet life is stubborn, and Proxima Centauri b might have a few tricks up its sleeve. If it has a thick atmosphere or a strong magnetic field, it could shield itself from the worst of its star's tantrums. Some scientists even speculate that the flares, while destructive, could spark chemical reactions in the atmosphere that create the building blocks of life. And here's another twist: tidally locked planets like this one, where one side always faces the star and the other plunges into eternal night, might still host life in the twilight border between scorching day and frozen darkness. Imagine a world where the only habitable zone is a thin ribbon of twilight, where rivers could flow beneath alien skies. The real mystery lies in what we haven't seen yet: an atmosphere. Detecting one would be a game-changer, revealing whether this neighboring world holds water vapor, oxygen, or even biosignatures hinting at life. Future telescopes might finally crack this puzzle, letting us peer across the interstellar void and answer the ultimate question. Could life exist just a cosmic stone's throw away? Proxima Centauri b is our first, best clue. Now imagine a planetary system so tightly packed that all 7 of its worlds could fit inside the orbit of Mercury. That's TRAPPIST-1, a faint red dwarf star 39 light-years away with a family of Earth-sized exoplanets dancing around it. Among them, TRAPPIST-1e stands out as the crown jewel, a rocky world bathed in dim crimson light where the conditions for life might just be perfect. This isn't just another exoplanet, it's a laboratory for understanding how life could arise in systems utterly unlike our own. What makes TRAPPIST-1e so intriguing isn't just its size, nearly identical to Earth, but its place in a cosmic ballet. All 7 planets orbit so close to their star that a year on TRAPPIST-1e lasts just 6 Earth days. Yet despite its proximity, the star's faint glow means the planet could still bask in temperatures mild enough for liquid water. But here's the catch: like Proxima Centauri b, it's probably tidally locked, with one side perpetually facing the star in scorching daylight and the other shrouded in frozen night. Life here, if it exists, would cling to the twilight boundary, a narrow band where temperatures might allow rivers to flow and chemistry to stir. NASA James Webb Space Telescope has already begun probing TRAPPIST-1e's atmosphere, hunting for traces of water vapor, carbon dioxide, or even methane gases that could hint at a biosphere. Early observations suggest the planet might lack the thick hydrogen veil of a gas giant, raising hopes for a rocky, Earth-like atmosphere. But red dwarfs are unpredictable landlords, prone to flares that could strip away protective layers of air. If TRAPPIST-1e has weathered these storms, it might have done so by developing a robust magnetic field or replenishing its atmosphere through volcanic activity. The real magic of this system lies in its siblings. With 7 planets packed so close together, each one's gravity tugs on the others, creating tidal forces that could heat their interiors, like Jupiter's moons Europa and Io, but on an interstellar scale. This tidal heating might keep subsurface oceans liquid, even on worlds far outside the traditional habitable zone. Imagine an entire system where life could arise not just on one planet, but on multiple, each with its own unique brand of biology, separated by just millions of miles instead of light years. TRAPPIST-1e offers a glimpse into a future where we might compare not just individual exoplanets, but entire planetary families. If life thrives here, it could mean the universe is teeming with worlds where day never turns to night, where seasons are measured in orbits rather than tilts, and where the definition of habitable stretches far beyond what we once thought possible. Kepler-186 isn't just another exoplanet, it's a milestone in cosmic discovery. When astronomers confirmed its existence in 2014, it became the first Earth-sized world ever found snugly within its star's habitable zone. Picture a planet only 10% larger than our own, basking in the faint crimson glow of a red dwarf star 500 light-years away. Its discovery shattered assumptions, proving that planets like ours could exist around stars utterly different from the Sun. What makes this world so fascinating isn't just its size. It's the tantalizing possibility of alien photosynthesis. Kepler-186 orbits its star at just the right distance to allow liquid water, the universal solvent of life. But here's the twist: its sun is a dim red dwarf, bathing the planet in light that's richer in infrared than our yellow sunlight. For Earth-like plants, this would be like trying to grow under a perpetual sunset. Yet life adapts. If vegetation exists here, it might evolve pigments unlike anything on Earth, perhaps deep blacks or violets to absorb every scrap of that ruddy glow. Imagine forests with leaves darker than charcoal, stretching toward a star that hangs motionless in a forever twilight sky. The planet's gravity would feel familiar, only slightly stronger than Earth's, but its seasons would be alien. Tidally locked like so many red dwarf worlds, one side might be scorched by eternal day while the other languishes in frozen darkness. But between these extremes, along the Terminator line, conditions could be just right for liquid water to pool and flow. And if Kepler-186f has an atmosphere thick enough to distribute heat, life might cling to patches of habitability far beyond that narrow band. The real intrigue lies in the chemistry. Red dwarfs emit fierce ultraviolet radiation in their youth, which could break apart water molecules and strip away atmospheres. But if this planet held onto its air or regenerated it through volcanic activity, it might now host a stable climate. Future telescopes could analyze its atmosphere for biosignatures like oxygen or methane, gases that on Earth are almost always tied to life. Finding them here would suggest that photosynthesis isn't just a fluke of our solar system, it could be a universal strategy for turning starlight into survival. Kepler-186f challenges us to rethink the boundaries of habitability. If life thrives here under a star so different from our own, it means the cosmic recipe for biology might be far more flexible than we ever imagined. This isn't just a planet. It's a test case for how diverse life-bearing worlds can truly be. Deep in the constellation Cetus, 49 light-years from Earth, a super-Earth named LHS 140b defies expectations. This isn't just another rocky world, it's a cosmic fortress, a planet so dense that its gravity could hold onto an atmosphere for billions of years. Imagine a place twice Earth's size but nearly 7 times more massive, where a thick blanket of air presses down on towering mountain ranges and vast sheltered oceans. Unlike the violent flares of Proxima Centauri, LHS 140b's star is unusually calm for a red dwarf, offering a rare stable environment where life might have had the time and peace to emerge. What sets this world apart is its potential to harbor water, not just in fleeting patches but in planet-spanning quantities. Its dense atmosphere acts like a pressure cooker, trapping heat and moisture close to the surface. Some models suggest it could host a global ocean deeper than Earth's, sealed beneath layers of air thick enough to shield it from space. Picture a twilight world where the sun never moves in the sky, casting perpetual crimson hues over swirling storms and steaming seas. The planet's gravity would make every step feel like wading through syrup, but for life adapted to such conditions, this could be a paradise. The star's stability is the real wild card. Most red dwarfs unleash deadly flares in their youth, but LHS 140's star is a quiet elder, its tantrums long past. This means the planet's atmosphere, if it survived the early chaos, could have persisted for eons, giving chemistry ample time to brew complexity. Recent studies hint at traces of nitrogen and oxygen in its air, gases that on Earth are hallmarks of life, but the most tantalizing clue lies in its temperature, smack in the middle of the habitable zone, where water could exist as a liquid, a solid, and a gas all at once. Future telescopes might soon glimpse the planet's atmosphere in detail, searching for the telltale fingerprints of biology, perhaps even industrial pollutants hinting at civilizations. LHS 140b isn't just a candidate for life, it's a time capsule, a world where the conditions for biology might have persisted longer than Earth. If life thrives here, it could mean the universe is quieter, older, and far more patient than we ever imagined. Hundreds of light years away in the constellation Lyra, Kepler-442b orbits a star that's neither too hot nor too cold, a Goldilocks sun just right for nurturing life. This isn't just another exoplanet, it's one of the most Earth-like worlds ever discovered, scoring a staggering 0.84 on the Earth Similarity Index. To put that in perspective, Mars, a planet we've long dreamed of terraforming, only manages 0.64. Kepler-442b isn't merely in the habitable zone. It's a near-perfect cosmic mirror of our own world, with a size, temperature, and even starlight eerily reminiscent of home. What makes this planet so special starts with its sun, a K-type star, older and milder than our own. Unlike the violent red dwarfs that bombard their planets with flares, this orange-hued star offers a steady glow, bathing Kepler-442b in sunlight just 20% dimmer than Earth. That subtle difference could mean seasons slightly longer and winters a touch colder, but well within the range where life could adapt. The planet's orbit takes 112 Earth days, a leisurely year spent circling a sun that hangs in the sky like a persistent amber ember. But the real magic lies beneath the surface, literally. Kepler-442b is likely a rocky world with a mass about twice Earth's, meaning its gravity would feel familiar yet firm, like carrying a heavy backpack everywhere you go. That extra heft could be a blessing. Stronger gravity helps planets retain atmospheres longer, shielding them from stellar winds. Models suggest this world might have active plate tectonics, recycling nutrients and stabilizing climates over eons, a critical ingredient for complex life. The clincher, light conditions perfect for photosynthesis. While red dwarf planets struggle with dim, crimson skies, Kepler-442b's star emits enough visible light that Earth-like plants could theoretically thrive here. Imagine forests bathed in perpetual golden hour, where leaves angle toward an orange sun that never quite reaches the brilliance of our own, yet mysteries remain. We don't yet know if this near twin has an atmosphere or water, though the math suggests it should. Future telescopes might soon catch whispers of water vapor or even oxygen in its air. If they do, Kepler-442b could leap from potentially habitable to potentially inhabited, a world where the line between science and science fiction blurs beneath an alien sun. Only 14 light-years from Earth, close enough that future generations might glimpse it through telescope lenses. Wolf 1061c spins in quiet orbit around a restless red dwarf. This isn't just another habitable zone candidate. It's a world of extremes where the possibility of life hinges on a delicate balancing act between its solid, Earth-like bulk and the temper tantrums of its unpredictable star. At 1.4 times Earth's mass, Wolf 1061c falls into the coveted super-Earth category, large enough to hold onto a thick atmosphere, yet small enough to avoid becoming a gaseous mini-Neptune. What makes this planet so intriguing is its precarious perch in the habitable zone's inner edge. Orbiting its star every 18 days, it basks in just enough warmth for liquid water, but one step closer and its oceans would boil away. Unlike the gentle, steady glow of our sun, Wolf 1061 star is a flickering candle, prone to sudden flares that can double its brightness in minutes. These violent outbursts blast the planet with X-rays and ultraviolet radiation, the kind that could shred atmospheres and sterilize surfaces, yet life might still find a way. The planet's saving grace could be its sheer heft. That extra mass means stronger gravity, which helps cling to protective layers of air even under stellar assault. Simulations suggest Wolf 1061c might have built a robust carbon dioxide atmosphere, a natural greenhouse blanket that redistributes heat and shields the surface from radiation. Picture a world where the sky glows faintly red, where dense air muffles sound and slows winds, and where deep valleys might cradle sheltered pools of water far from the storms raging above. But here's the twist: tidal locking. Like most planets orbiting red dwarfs, one side of Wolf 1061c likely faces eternal day, the other eternal night. The day side might bake under relentless stellar flares, while the night side freezes solid, but between them, along the Terminator line, there could be a ribbon of twilight stability. In this narrow band, temperatures might hover just right for liquid water, creating a ring of habitability wrapped around the planet like a cosmic equator. The real test will come when next-generation telescopes analyze its atmosphere. If they spot water vapor or ozone, it would suggest this world has somehow weathered its star's fury. Wolf 1061c reminds us that habitable doesn't always mean hospitable, but where there's stability, even in slivers, life might just take root. Gliese 667cc sounds like something out of a sci-fi epic, and in many ways it is. Orbiting not one, not two, but 3 stars 22 light-years from Earth, this super-Earth defies the very definition of a stable solar system. Picture a planet 4 times heavier than our own, bathed in the shimmering glow of its triple suns, 2 orange dwarfs and a red dwarf locked in an intricate gravitational dance. Most days, only the dimmest star, Gliese 667c, looms large in its skies, casting a pale reddish light. But occasionally, the other 2 suns pierce the horizon like distant fiery marbles, painting the clouds with alien hues. What makes this world a prime candidate for life isn't just its place in the habitable zone, it's the sheer resilience it would need to survive there. Despite the chaotic stellar trio, Gliese 667c's orbit remains steady, tracing a path that keeps it just far enough from its primary star to avoid tidal locking. That means it could rotate like Earth, offering day-night cycles instead of eternal twilight. Models suggest surface temperatures might hover around a comfortable 280 degrees Kelvin, cool enough for liquid water if any exists. And with a rocky composition likely similar to Earth's, this planet could have continents, mountains, even weather systems cycling beneath its triple-star skies. But the debates rage on. Some astronomers argue Gliese 667c might be more Venus than Earth, a hothouse drowning under a thick carbon dioxide atmosphere where runaway greenhouse effects bake the surface. Others speculate it could be a water world, its extra mass allowing it to cling to vast, globe-spanning oceans beneath hydrogen-rich air. Then there's the radiation question. Red dwarfs, like its primary star, are notorious for their youthfully violent phases. If Gliese 667c endured those early eons, it might now enjoy a quieter middle age, its atmosphere, if it survived ripe for nurturing chemistry. The most tantalizing clue came from early spectroscopic studies hinting at water vapor in its air. But with current technology, we're still squinting through a keyhole at this world. Future telescopes might finally answer whether those whispers of moisture signal oceans, ice caps, or just atmospheric traces. For now, Gliese 667c stands as a cosmic paradox, a planet where the ingredients for life exist amid stellar chaos, challenging us to rethink how delicate or durable habitability truly is. 1,200 light-years from Earth, drifting in the constellation Lyra, a world named Kepler 62f paints a haunting portrait of what an ocean planet might look like on a cosmic scale. Imagine an Earth-sized world just 40% larger than our own, circling a star slightly cooler and smaller than the Sun, its years measured in 267 languid Earth days. What sets this planet apart isn't just its place in the habitable zone, but the shimmering possibility that its entire surface could be a single, unbroken ocean. Kepler 62f orbits at the outer edge of its star's Goldilocks zone, where sunlight is faint but not frigid. At this distance, temperatures might hover just above freezing unless something extraordinary is at work. Here's where the theories ignite. If this planet has a thick hydrogen-rich atmosphere, its greenhouse effect could trap enough heat to maintain liquid water across its entire surface. Picture a global sea deeper than Earth's Pacific, stretching from pole to pole without a single rocky shoreline. Storms would roll across endless waves, their patterns dictated by Coriolis forces far stronger than ours, thanks to the planet's higher density and gravity. Beneath those waves, pressures could crush submarines like tin cans, yet hydrothermal vents might dot the abyssal plains, steaming geysers of chemistry where life could cling. But there's another possibility, one that's even stranger. Some models suggest Kepler 62f might be a snowball world, its oceans capped by a miles-thick shell of ice. Yet even here, hope isn't lost. Europa, Jupiter's icy moon, teaches us that subterranean oceans can thrive under frozen surfaces, heated by tidal forces or radioactive decay. If Kepler 62f has similar geologic activity, its icy crust could hide a labyrinth of liquid water caves, lit by bioluminescent organisms adapted to eternal darkness. The real enigma lies in the planet's composition. Its radius suggests a rocky core, but the sheer volume of potential water up to dozens of times Earth's oceanic reserves hints at a world formed farther out in its system, where ice was plentiful before migrating inward. That journey could have delivered organic molecules to its depths, priming the waters for chemistry. Future telescopes might one day glimpse the glint of sunlight off Kepler-62f's hypothetical oceans or detect water vapor in its air. Until then, it remains a celestial riddle, a world where the definition of Earth-like stretches to include planets with no Earth at all. Imagine a world where the sky isn't blue, but a deep, hazy pink, where the air is thick with hydrogen, and beneath it, an ocean stretches further than the eye can see. This isn't science fiction, it's K2-18b, a planet 120 light-years away that redefines what habitable could mean. In 2019, astronomers made history when they spotted water vapor swirling in this super-Earth's atmosphere, the first time we'd ever detected water on a potentially habitable exoplanet. But K2-18b isn't just another rocky world. It's the prototype for an entirely new class of planets, Haitian worlds, where hydrogen-rich atmospheres blanket globes spanning oceans. At 8.6 times Earth's mass, K2-18b straddles the line between rocky super-Earth and gaseous mini-Neptune. Its surface gravity would crush human bones, but for life evolved in its depths, that crushing pressure might be a cradle. The planet's thick hydrogen atmosphere acts like a cosmic pressure cooker, trapping heat so efficiently that even though it orbits closer to its star than Mercury does to our Sun, its surface could be drenched in liquid water instead of scorched rock. Picture an ocean not confined to basins but wrapping the entire planet, an unbroken expanse where storms stir waves taller than skyscrapers and tides are pulled not by a moon but by the star itself. The real breakthrough came when the James Webb Space Telescope peered into K2-18b's air and found more than just water vapor. There were whispers of dimethyl sulfide, a molecule on Earth produced almost exclusively by living organisms like phytoplankton in our oceans. Now, this isn't proof of alien algae, not yet. That signal could also come from volcanic activity or other non-biological processes, but the mere possibility sent shockwaves through the scientific community. For the first time, we were staring at a world where the chemistry of life as we know it might already be underway. Haitian planets like this one force us to rethink the rules. On Earth, life thrives in sunlight and oxygen, but in K2-18b's eternal twilight, organisms might metabolize hydrogen or thrive near hydrothermal vents in pitch-black seas. The planet's star, a quiet red dwarf, bathes it in infrared light useless to Earth's plants, but perhaps harnessable by alien life forms with pigments we can't even imagine. And because hydrogen atmospheres are so light-trapping, even planets far from their stars could stay warm enough for liquid water, expanding the habitable zone to regions we'd once written off as frozen wastelands. The next step, searching for more biosignatures, not just water, but ozone, methane, or that tantalizing dimethyl sulfide signal again, clearer this time. K2-18b isn't just a planet, it's a doorway. If life thrives here under a pink sky and in hydrogen-rich seas, it means the universe could be brimming with habitable worlds we've barely begun to dream of. 12 light-years from Earth, so close that its star is visible through backyard telescopes, Teegarden Star B quietly defies the odds. This unassuming world, barely heavier than our own, circles one of the calmest red dwarfs ever discovered, a stellar recluse emitting almost no flares or harmful radiation. While most planets orbiting red dwarfs face constant bombardment, Teegarden Star B exists in rare cosmic harmony with its host, offering a glimpse of what stability might look like on an alien world. Orbiting snugly within its star's habitable zone, this Earth-mass planet completes a year in just 4.9 Earth days, so close that its sun would loom 10 times larger in its sky than ours does. Yet despite this proximity, the star's feeble glow means surface temperatures could hover near Earth-like averages if the planet has an atmosphere to distribute heat. That's the first puzzle. T-Godden's star is so dim and cool that liquid water might exist even on planets hugging it tightly. Picture a world where the sun hangs low and red, casting permanent twilight across rolling plains or tranquil seas, with no violent flares to scorch the landscape or strip away protective layers of air. The star's tranquility is the real game-changer. Most red dwarfs spend their youth erupting in cataclysmic flares, but T-Godden's star is ancient, at least 8 billion years old, with its turbulent days long past. This extended calm could have given the planet's atmosphere, if it ever had one, time to stabilize rather than evaporate. Unlike the radiation-blasted surfaces of younger systems, T-Godden's star B might have enjoyed eons of gentle conditions, allowing chemistry to evolve uninterrupted. But tidal locking looms large. Like nearly all planets orbiting red dwarfs, one side likely bakes in eternal daylight while the other freezes in endless night. The saving grace, that thick atmosphere we keep mentioning. If present, it could ferry warmth from day to night, creating habitable patches beyond the twilight borderline. Some models even suggest weather patterns so efficient that entire hemispheres might avoid temperature extremes, with hurricanes the size of continents redistributing heat like a planetary circulatory system. The mysteries compound when we consider water. Red dwarfs form surrounded by ice-rich material, meaning T-Godden's star B could have been born with abundant frozen reserves. As the star warmed during its youth, those ices might have melted into oceans that, shielded from radiation, could still persist today. Future telescopes might detect signs of that moisture, either as vapor in the air or as glinting surface reflections. T-Godden's star B challenges our biases about red dwarf planets. We assume they're radiation-scarred wastelands, but this world whispers another possibility: sheltered, serene, and just maybe a haven for life that's been quietly thriving right under our cosmic nose. GJ357 D isn't your typical habitable zone candidate, it's a cosmic paradox. Orbiting a dim red dwarf 31 light-years away, this super-Earth sits just on the edge of its star's Goldilocks zone, where sunlight is so feeble that surface temperatures likely hover around -64 degrees Fahrenheit. By all rights, it should be a frozen wasteland, yet scientists can't shake the tantalizing possibility that beneath its icy shell, rivers of liquid water might still flow, not because of starlight, but thanks to the planet's own fiery heart. At 6 times Earth's mass, GJ357 D has gravity strong enough to hold onto a thick atmosphere, one that could act like a planetary pressure cooker. Carbon dioxide or methane trapped in its air might create a greenhouse effect potent enough to keep pockets of water liquid despite the chill. But the real game changer lies deeper: tidal heating. Gravitational tugs from its star and neighboring planets could be flexing GJ357 D's core like a cosmic stress ball, generating enough internal heat to fuel volcanic vents or even subsurface oceans. Picture hydrothermal systems similar to those in Antarctica's Lake Vostok or beneath Iceland's glaciers, where microbes thrive without sunlight. Just swap Earth's ice for alien permafrost and our familiar geology for who knows what alien chemistry. The kicker: this planet might be more than just a frozen world with warm guts. Some models suggest its thick atmosphere, if it exists, could redistribute heat efficiently enough to create temperate oases on the surface. Imagine ice caves where geothermal warmth melts underground reservoirs, their ceilings dripping with condensation, while outside, hydrocarbon snow falls silently under a dim red sun. Current telescopes can't yet confirm whether GJ357 D has an atmosphere or active geology, but if future observations detect infrared heat signatures or atmospheric gases like carbon dioxide, it would transform this icy outlier into a prime candidate for extremophile life. GJ357 D challenges us to rethink the very definition of habitable, proving that sometimes the warmth for life doesn't come from above but from below. 44 light-years away, tucked in the constellation Pictor, HD 40307, G spins in quiet mystery, a planet caught between two identities. Is it a super-Earth, a colossal rocky world with towering mountains and deep valleys? Or is it a mini-Neptune, shrouded in thick hydrogen and helium with no solid surface at all? This enigma makes it one of the most fascinating habitable zone candidates we've found. At nearly 7 times Earth's mass, it's right on the edge where planets transition from terrestrial behemoths to gaseous dwarfs, and that ambiguity holds the key to whether life could exist there. What we do know is this: HD 40307, G orbits its orange dwarf star at just the right distance for liquid water if conditions align. A year here lasts 197 Earth days, placing it comfortably in the star's habitable zone. But here's where things get complicated. If the planet is a mini-Neptune, its crushing atmospheric pressure and lack of a defined surface would render it hostile to life as we know it. Picture an endless veil of toxic haze where temperatures and pressures rise to lethal levels long before you'd reach anything solid. Yet if it's a super-Earth, that same mass could be a blessing. Strong gravity might anchor a breathable atmosphere, while geothermal activity from its hefty core could fuel hydrothermal vents teeming with chemistry. The debate hinges on a critical factor: the planet's density. A mini-Neptune would puff up like a cosmic marshmallow, its radius bloated by light gases. A super-Earth, though, would be compact and dense, its bulk squeezed into a smaller silhouette. Current observations lean tantalizingly toward the latter, suggesting HD 40307 G might indeed be rocky. But there's a twist: this world could still wear a thick cloak of gases, turning its surface into a pressure cooker. Imagine an ocean trapped under an atmosphere 10 times thicker than Earth's, where the sky glows orange from perpetual refraction and the air hums with the weight of 1,000 storms. The star itself adds another layer of intrigue. Orange dwarfs like HD 40307 are often called Goldilocks stars, not as tempestuous as red dwarfs, not as short-lived as blue giants. They burn steadily for tens of billions of years, offering planets like this one ample time for life to emerge. And unlike tidally locked red dwarf worlds, HD 40307 G likely rotates, granting it Earth-like day-night cycles. That rotation could stir its atmosphere into stabilizing weather patterns, preventing the extreme temperature swings that plague one-sided worlds. The ultimate question, though, is water. Could it pool here? If the planet is a super-Earth with plate tectonics, moisture might rise from volcanic outgassing or arrive via icy comets, collecting in vast seas. Alternatively, a hydrogen-rich mini-Neptune scenario might allow liquid water only in an abstract sense, deep in the atmosphere where pressures and temperatures align, forming droplets that never touch ground. Future telescopes could settle the debate by analyzing starlight filtering through the planet's atmosphere, hunting for traces of water vapor, methane, or even oxygen. HD 40307 G forces us to confront the blurry line between rocky and gaseous, between habitable and hostile. It's a reminder that nature doesn't always fit our categories, and that the most promising worlds might be the ones that defy easy explanation. Kepler 452b isn't just another exoplanet, it's the closest thing we've found to a mirror of Earth orbiting another star. Picture a world 60% larger than our own, circling a sun almost identical to ours, but with one crucial difference: age. This star, Kepler 452, has been burning for 6 billion years, 1.5 billion years longer than our own sun. That extra time could mean everything for life. Imagine a planet where evolution has had an additional cosmic eon to experiment, where civilizations might have risen and fallen long before humans even walked the Earth. The numbers alone make this world extraordinary. Kepler-452b's orbit lasts 385 Earth days, just 20 days longer than ours, placing it squarely in the habitable zone where liquid water could pool on its surface. Its sun shines only 10% brighter than ours, casting familiar golden light over landscapes that might include continents, oceans, even weather patterns not so different from home. But here's where the parallels get eerie. Based on its size and composition, this planet likely has active plate tectonics, recycling minerals and stabilizing its climate over geological timescales, a key ingredient for complex life. Yet the differences could be just as revealing. That older star means Kepler-452b receives slightly more solar radiation than Earth, raising the stakes for its atmosphere. A thick carbon dioxide blanket could have built up over time, triggering a runaway greenhouse effect like Venus. Alternatively, life might have adapted to the changing conditions, evolving photosynthesis that thrives under stronger sunlight. The planet's higher gravity would shape its ecosystems to taller, denser plants to withstand the pull, or animals with robust skeletal structures to navigate a world where everything weighs nearly twice as much. The most tantalizing question isn't just whether life exists there now, but what stage it might have reached. On Earth, 6 billion years was enough for single-celled organisms to evolve into spacefaring civilizations. If Kepler-452b followed a similar trajectory, its biosphere could be unimaginably advanced, or perhaps already exhausted, its resources spent by a species that flourished and vanished in our cosmic infancy. Current telescopes can't yet detect signs of technology or city lights, but future instruments might scan its atmosphere for industrial pollutants or artificial molecules. Kepler-452b is more than a scientific curiosity. It's a time capsule showing us a possible future for our own planet as the sun ages and brightens. Studying this world isn't just about finding aliens. It's about glimpsing Earth's destiny written in the light of an older, wiser star. Just 11 light-years from Earth, so close that its star is visible through amateur telescopes, Ross 128b offers a rare glimpse of serenity in the turbulent realm of red dwarf planets. While most worlds orbiting these small, fiery stars endure relentless radiation storms, this Earth-sized oasis circles one of the calmest red dwarfs ever discovered, a star so placid it barely flickers. Picture a planet where the sun rises each morning without erupting in deadly flares, where the sky might hold steady for eons instead of being shredded by stellar tantrums. That stability makes Ross 128b one of our best bets for finding life-friendly conditions beyond our solar system. What sets this world apart is its star's unusual temperament. Unlike Proxima Centauri or TRAPPIST-1's violent hosts, Ross 128 is a cosmic meditation master, an old, slow-spinning red dwarf that has left its fiery youth behind. Observations reveal almost no flare activity, meaning its planet faces minimal atmospheric stripping and surface radiation. That's critical because red dwarfs typically bombard their planets with enough X-rays to sterilize continents, but Ross 128b might have enjoyed billions of years of uninterrupted calm. If it holds an atmosphere still a big if, that air could be rich in life-friendly gases like nitrogen or carbon dioxide, gently warmed by starlight just 20% as strong as our sun's. Size matters here too. At only 1.35 times Earth's mass, Ross 128b almost certainly has a rocky surface, possibly with active geology to recycle nutrients and regulate climate. Its gravity, slightly stronger than ours, would help cling to any atmosphere while still allowing mountain ranges and valleys to form. But the real fascination lies in its orbit, a tight 20-day year that keeps it tidally locked. One side forever faces its dim crimson sun, the other endless night. Yet models suggest that with a thick enough atmosphere, heat could spread across the terminator line, creating a twilight belt where temperatures hover near Earth like averages. The ultimate question is water. red dwarfs form surrounded by ice-rich material, and Ross 128b's tranquil history means any primordial oceans might have persisted. Imagine a world where rain falls in slow motion under weak gravity, where rivers carve valleys under a sun that never moves in the sky, and where life, if it exists, has had twice as long as Earth's biosphere to evolve under stable conditions. Future telescopes could soon scan its atmosphere for water vapor or methane, but even without confirmation, Ross 128b stands as a quiet rebel, proving not all red dwarf planets are cosmic battlegrounds. Some might just be peaceful places to grow old beneath a gentle red sun. Hidden within the faint glow of a red dwarf star 100 light-years away, TOI-700d presents one of the most compelling cases for a habitable Earth-sized world ever discovered. When NASA test mission spotted it in 2020, this planet shattered expectations not just because it's rocky and orbits squarely in its star's Goldilocks zone, but because climate models suggest it could host liquid water even while being tidally locked. Picture a world where one hemisphere bakes under eternal daylight, the other languishes in endless night, and yet somewhere between them, a sliver of stability might exist where life could cling. What makes TOI-700d extraordinary starts with its star. Unlike many red dwarfs that rage with flares, TOI-700 is a quiet celestial neighbor emitting steady, gentle radiation. This stability allows the planet to potentially retain an atmosphere critical for distributing heat across its locked faces. Climate simulations reveal something astonishing. With the right mix of gases like carbon dioxide and nitrogen, air currents could ferry warmth from the dayside to the nightside, preventing the entire planet from freezing solid or overheating. Imagine swirling cyclones the size of continents acting as planetary thermostats, their winds carving habitable pockets along the twilight zone where temperatures might hover near 70 degrees Fahrenheit. Then there's the water question. Test data hints at a world slightly larger than Earth, likely rocky, but with a density suggesting significant water content. Some models propose TOI-700d could be an eyeball planet, a term scientists use for tidally locked worlds where the dayside melts into a vast ocean while the nightside remains encased in ice. In this scenario, the Terminator line might host a ring of lush, tempestuous shores, where waves from the sunlit side crash against glaciers under a sky permanently streaked with crimson clouds. But the real breakthrough came from three-dimensional climate models. Unlike earlier simulations that assumed simple atmospheres, these advanced calculations factor in ocean currents, cloud cover, and even topography. The results, TOI-700d could maintain liquid water across far more of its surface than previously thought, not just in narrow strips but in sprawling temperate bands. Clouds forming over the dayside ocean might reflect enough sunlight to prevent runaway greenhouse effects, while nightside ice sheets could stabilize the climate like planetary air conditioners. The intrigue deepens when we consider chemistry. Red dwarfs emit light mostly in infrared, which interacts differently with water and air than our sun's visible spectrum. If life exists here, it might rely on pigments tuned to harness those longer wavelengths, painting hypothetical forests in deep blacks or purples to absorb every photon available. Photosynthesis wouldn't look green, it might not even look like anything we'd recognize. TOI-700d stands as a testament to how much we've learned and how much remains unknown. Future telescopes could analyze its atmosphere for biosignatures like oxygen or methane, but even without confirmation, this world has already reshaped our understanding of habitability. It proves that even planets forever bound to their stars, with one face always in light and the other in darkness, might still carve out niches where life could thrive. In the silent ballet of cosmic forces, TOI-700d whispers that stability isn't about symmetry, it's about balance. Buried in a mountain of old Kepler telescope data, almost lost forever in the digital noise, Kepler-1649c wasn't just discovered, it was resurrected. Years after NASA's Kepler mission ended, scientists poring over archived readings spotted something extraordinary: a planet whose signal had been misclassified by algorithms as false noise. When human eyes finally caught the error, they uncovered one of the most Earth-like worlds ever found, a rocky gem orbiting squarely in its star's habitable zone, just 300 light-years away. This cosmic near-twin is barely 6% larger than Earth, making it one of the few exoplanets with almost identical bulk and gravity. But it's not just size that excites astronomers, it's location. Kepler-1649c circles its red dwarf star every 19.5 Earth days, soaking in 75% of the sunlight Earth receives. That delicate balance places it firmly in the Goldilocks zone, where temperatures could allow water to pool on its surface without boiling or freezing away. Picture a world where the sun hangs perpetually low in a crimson sky, casting long shadows over landscapes that might mirror our own rolling hills, shallow seas, even continents veined with rivers. Yet the star here plays a tricky role. Like most red dwarfs, it's prone to flares, violent eruptions that could strip atmospheres or bombard surfaces with radiation. But Kepler-1649c has two potential shields. First, its orbit is slightly elliptical, which might help it avoid the worst stellar outbursts by dancing just outside their usual reach. Second, models suggest it could have a magnetic field stronger than Earth's, deflecting deadly particles like an invisible fortress. The real mystery lies in whether these defenses have held up over time. The planet's rediscovery is a lesson in scientific humility. Originally dismissed by automated filters, it took a team of volunteers with the Kepler False Positive Working Group to recognize the faint, rhythmic dip in starlight for what it was, a world hiding in plain sight. Their persistence hints at something profound. We might have already collected data on other Earth twins, their signals still buried in old hard drives like messages in cosmic bottles. What's next? The James Webb Space Telescope could soon analyze Kepler-1649c's atmosphere for signs of water or oxygen. But even without confirmation, this world stands as a beacon, proof that sometimes the most extraordinary discoveries aren't just found in the depths of space, but in the patience to look twice. GJ1214b isn't just an exoplanet, it's a cosmic enigma wrapped in steam. Located just 40 light-years away in the constellation Ophiuchus, this world defies easy categorization, hovering somewhere between a waterlogged super-Earth and a gaseous mini-Neptune. Picture a planet 2.7 times the size of our own, but with a mass nearly 7 times greater, a density that screams water world, but not the kind we're used to. Here, oceans might not lap against rocky shores, but instead stretch endlessly beneath a crushing atmosphere hundreds of times thicker than Earth's, where the very concept of surface blurs into a haze of superheated steam and exotic ices. What makes GJ1214b so baffling is its atmosphere, or more accurately, our inability to see through it. When astronomers first studied this world, they expected to detect clear chemical signatures as starlight filtered through its air. Instead, they found nothing. The planet's veil is so uniformly opaque that it absorbs almost all light passing through, creating a flat, featureless spectrum that gives no clues about what lies below. Some theories suggest this could mean an atmosphere choked with water vapor or methane, while others propose a high-altitude layer of photochemical haze like Titan's smog but infinitely denser. Imagine a global greenhouse so intense that sunlight never reaches the hypothetical ocean below, leaving any potential life to thrive in perpetual darkness near hydrothermal vents or within layers of pressurized lukewarm fluid. Then there's the temperature problem. Orbiting its red dwarf star every 38 hours, GJ1214b is tidally locked and broiling surface estimates hover around 400 degrees Fahrenheit. That's too hot for liquid water on Earth, but under the extreme pressures of this planet's deep atmosphere, water could exist in a bizarre supercritical state, neither fully liquid nor gas. Picture an ocean that behaves like steam and liquid simultaneously. Its molecules packed so tightly they dissolve minerals and organic compounds with eerie efficiency. Life here, if it exists, might resemble the extremophiles near Earth's deep-sea vents, but adapted to pressures that would crush submarines like soda cans. The real puzzle lies in the planet's origins. Did it form farther out in its system, where ice was plentiful, before migrating inward and melting into a global deluge? Or was it born with a hydrogen-helium envelope that somehow transformed into this steamy shroud? The James Webb Space Telescope could soon crack this mystery by analyzing infrared light for traces of molecules like water or ammonia. But even with answers, K2-18b will remain a testament to nature's creativity, a world where the rules of habitability rewrite themselves under the weight of an alien sky. HD85512b sits 36 light-years away in the constellation Vela, a super-Earth that redefines how we picture habitability around active stars. At 3.6 times Earth's mass, this planet orbits perilously close to its orange dwarf sun, so close that a year lasts just 58 Earth days. But here's the twist: despite its tight orbit, HD85512b might be one of the best candidates for a stable, life-friendly climate we've ever found, thanks to an unexpected hero clouds. Unlike the violent red dwarfs that dominate exoplanet discoveries, this star is a quieter K-type, offering a gentler radiation environment, yet the real magic lies in the planet's potential atmospheric dynamics. Climate models suggest something extraordinary. With just 50% cloud cover, HD85512b could reflect enough sunlight to prevent runaway greenhouse heating, balancing its energy budget like a planetary thermostat. Picture a world where perpetual overcast skies act as a global sunshade, diffusing the star's warmth evenly across the surface instead of letting it bake the ground unchecked. These aren't Earth-like cumulus clouds, though. They might be sulfuric acid or salt crystal formations, swirling in alien patterns we've yet to imagine. The planet's eccentric orbit adds another layer of intrigue. Unlike Earth's near-circular path, HD85512b follows a slightly elliptical route, alternately dipping closer to and pulling away from its star. This rhythmic dance could create seasonal shifts in temperature, but here's where clouds play double duty, expanding during warmer periods to block excess heat, then thinning as the planet cools to trap precious warmth. It's a self-regulating system more sophisticated than anything we've engineered on Earth. But could water exist here? The answer hinges on that delicate cloud equilibrium. Too few clouds and the planet's oceans would evaporate under the star's glare. Too many, and it might freeze into a global snowball. The sweet spot lies somewhere in between, a Goldilocks scenario where cloud cover and atmospheric pressure align to maintain liquid water. Some simulations even suggest tropical bands near the equator could host persistent storms, their rain cycles fueled by the star's gentle but steady energy. The ultimate question is whether HD85512b's atmosphere has the right ingredients for this balancing act. Future telescopes might detect traces of water vapor or carbon dioxide gases that could seed cloud formation and regulate climate over eons. For now, this world stands as a lesson in celestial moderation, proving that sometimes the difference between paradise and wasteland isn't distance from a star, but what floats in the sky above. Kepler-22b was a revelation when it was discovered in 2011, one of the first exoplanets ever found snugly within its star's habitable zone, and a beacon of hope in the early days of planet hunting. 600 light-years away in the constellation Cygnus, this world orbits a sun-like star every 290 days, basking in a similar amount of starlight as Earth. But here's the catch: Kepler-22b isn't the Earth twin we initially imagined. At 2.4 times the size of our planet, it straddles the line between super-Earth and mini-Neptune, a cosmic hybrid that forces us to rethink what habitable really means. What makes this world so tantalizing and so frustrating is its sheer ambiguity. Its radius suggests it could be a rocky planet shrouded in a thick, steamy atmosphere, or a gaseous world with no solid surface at all. Picture an ocean planet where the water isn't confined to basins but extends down thousands of miles, pressurized into exotic forms of ice at the depths. Or envision a hydrogen-helium envelope so dense that the very air becomes a liquid ocean, blending seamlessly into the planet's interior without a clear boundary between sky and ground. The truth might lie somewhere in between, a gas dwarf with a rocky core buried under layers of slushy water and supercritical fluids, where chemistry experiments on a planetary scale unfold in perpetual twilight. The star it circles adds another layer of intrigue. Unlike the red dwarfs dominating recent discoveries, Kepler-22b's sun is a G-type star, nearly identical to our own but slightly cooler and smaller. This means the planet receives about 25% less starlight than Earth does, putting it at the outer edge of the habitable zone. But if it has a thick atmosphere rich in greenhouse gases like carbon dioxide or methane, that air could trap just enough heat to maintain liquid water. Climate models suggest its average surface temperature, assuming an Earth-like atmosphere, would hover around -11 degrees Fahrenheit, chilly, but not impossible for extremophiles. The lingering mystery is composition. Without a precise mass measurement, we can't calculate its density, leaving us guessing whether it's a water world, a gas ball, or something entirely unexpected. Future telescopes might finally crack this puzzle by analyzing starlight filtering through its atmosphere, if it has one. Detecting molecules like water vapor or ozone would tilt the scales toward habitability, while signs of hydrogen would confirm a gaseous nature. Kepler-22b remains a cornerstone of exoplanet science precisely because it refuses to fit neatly into categories. It's a reminder that the universe doesn't care about our labels, and that the most promising worlds might be the ones that defy our expectations at every turn. While Proxima Centauri b basks in the warmth of its star's habitable zone, its sibling Proxima Centauri c tells a very different story, one written in ice and shadow. Orbiting the same turbulent red dwarf but 6 times farther out, this frozen world completes a year in nearly 5 Earth years, existing in perpetual deep freeze where surface temperatures likely plunge to -400 degrees Fahrenheit. Here, sunlight is so feeble it would appear as little more than an exceptionally bright star in an inky black sky. But don't let the cold fool you, this planet might hold secrets where we least expect them. Discovered in 2019, Proxima Centauri c defies expectations simply by existing. At roughly 7 times Earth's mass, it shouldn't have formed so far from its small, dim star, a region where traditional planet-building materials would have been scarce. Its very presence suggests planetary formation is more creative than we thought, possibly assembling from icy debris pushed outward by migrating gas giants. The planet's extreme distance makes it a fascinating contrast to its inner sibling. Where Proxima b might struggle to hold onto an atmosphere under stellar flares, Proxima c's remoteness offers protection. Its frigid environment could have preserved ancient ices and organic molecules untouched for billions of years, like a cosmic time capsule. The real intrigue lies beneath the ice. While the surface is almost certainly frozen solid, tidal heating from its star or radioactive decay in its core might maintain a subsurface ocean, a dark, salty abyss insulated by miles of ice. We've seen this phenomenon on moons like Europa and Enceladus in our own solar system, where hidden oceans churn under icy shells, potentially hosting hydrothermal vents that foster life without sunlight. Proxima C could amplify this concept on a planetary scale. Imagine a world where the only liquid water exists in lightless depths, under pressures so intense that the water itself takes on exotic crystalline forms near the ocean floor. Life here wouldn't rely on photosynthesis, but on chemosynthesis, drawing energy from chemical reactions between rock and water, perhaps thriving in ecosystems as alien as the planet itself. Then there's the atmosphere problem, or lack thereof. Most models suggest Proxima C is too cold to retain a substantial gaseous envelope, but some theories propose a thin nitrogen atmosphere slowly leaking into space, or even seasonal outgassing as subsurface heat warms pockets of ice. If present, these trace gases could create ephemeral weather patterns, with nitrogen frost settling across plains during winter and sublimating into wisps of vapor during rare warm spells. What truly captivates scientists is the possibility of exchange between Proxima B and C. During the system's chaotic early days, impacts might have launched debris from one planet to the other. If life ever arose on the warmer Proxima B, microbial hitchhikers could have ridden meteorites to seed Proxima C's oceans, meaning these two worlds, though separated by cosmic extremes, might share a biological heritage. Future missions could unveil these mysteries. Proxima C's wide orbit makes it a prime target for direct imaging, where next-generation telescopes might capture its faint glow and analyze reflected starlight for clues about surface composition. Until then, this frozen sibling remains a paradox, a world too harsh for life as we know it, yet too intriguing to dismiss. In the dark and cold, the universe often hides its most surprising gifts. TRAPPIST-1F doesn't just orbit its star, it dances on the edge of possibility. The fifth planet out in this extraordinary seven-world system, it's a celestial paradox, a world that might be drowning in water yet still simmering with geothermal heat. Picture a globe slightly smaller than Earth, but with such low density that scientists suspect its mass could be up to 25% liquid. Not just shallow seas, but oceans so deep they'd make our Mariana Trench look like a puddle, wrapping the entire planet in a shimmering saline shroud. What makes this world so captivating isn't just the water, it's the hidden furnace beneath. TRAPPIST-1F orbits close enough to its siblings that their gravitational tugs constantly flex its core, much like Jupiter's moons need Europa's interior. This tidal heating could be the planet's saving grace. While its surface might be frozen under an icy shell miles thick, below that barrier, friction from these cosmic stretchings might maintain a subsurface ocean warmer than Earth. Imagine hydrothermal vents gushing minerals into Inkai waters, their chemistry ripe for sparking life, no sunlight required. The planet's rocky seafloor could be riddled with such vents, creating a network of habitable pockets in the abyss. The star itself plays a supporting role in this drama. TRAPPIST-1 is so dim that even though the planet orbits just 6 million miles away, 10 times closer than Mercury to our Sun, it still receives less warmth than Mars. Without tidal heating, this would be a frozen wasteland. But here's the twist, that proximity also locks the planet's rotation, leaving one side perpetually facing the star while the other drowns in eternal night. The day side's ice might thin near the equator, creating a slushy boundary where water occasionally breaches the surface, while the night side's ocean could remain sealed under a continent-thick ice cap unless underground heat keeps it churning. Then there's the atmospheric wildcard. Red dwarfs like TRAPPIST-1 tend to blast planets with X-rays in their youth, potentially stripping away air. But if this world held onto even a thin carbon dioxide atmosphere, that gas could act like a blanket, trapping tidal heat and preventing global freezing. Some models suggest seasonal thaws where atmospheric pressure temporarily rises, allowing geysers to erupt through surface cracks before refreezing. The James Webb Space Telescope has already glimpsed hints of an atmosphere here, though whether it's thick enough for stability remains unclear. Future observations might detect chemical imbalances like excess oxygen or methane. that hint at biological activity beneath the ice. Until then, TRAPPIST-1F stands as a masterclass in celestial irony, a world that by all rights should be frozen solid, yet might just be one of the system's best bets for life, not despite its distance from the star, but because of the cosmic dance it shares with its siblings. Kepler 443b presents a cosmic tightrope act, a world teetering on the very edge of its star's habitable zone, where the difference between frozen wasteland and tolerable warmth hinges on a celestial balancing act. Orbiting a dim K-type star 1190 light-years away, this exoplanet faces challenges that would make even the hardiest Earth extremophiles shudder. Its orbit isn't the neat, circular path we're accustomed to in our solar system. Instead, it traces a stretched ellipse swinging close enough to its star to briefly thaw before hurtling back into the deep freeze. Picture a planet caught in a perpetual cycle of climatic whiplash, where summers might bring fleeting pools of liquid water, only for winters to lock everything under mile-thick ice. What makes this borderline status so precarious is the physics of its orbit. Kepler 443b's eccentric path means the amount of starlight it receives fluctuates wildly, by up to 30% over its 240-day year. For comparison, Earth's orbital variation brings just a 7% change in solar energy. That inconsistency wreaks havoc on climate stability. During its closest approach, the planet basks in a surge of warmth that could melt surface ice. But this period lasts mere weeks before the long slide outward begins, temperatures plummeting as the star shrinks to a dim ember in the sky. Any life forms here would need survival strategies beyond anything we've seen, perhaps organisms that lie dormant for years, only metabolizing during those brief, golden intervals of moderation. The star itself adds another layer of complexity. K-type dwarfs like Kepler 443's Sun are steadier than the flaring red dwarfs that dominate exoplanet discoveries, but they're also significantly dimmer than our Sun. This means the planet's average position in the habitable zone is already skating on thin ice, literally. Climate models suggest that without an exceptionally thick atmosphere rich in greenhouse gases, its oceans would freeze solid during the cooler phases of its orbit. Yet an atmosphere thick enough to retain heat might also smother the surface under crushing pressure, creating a Venus-like hothouse during the close approaches. The slim chance for life here hinges on two fragile possibilities. First, tidal heating, the gravitational flexing caused by its elliptical orbit, might supplement the meager starlight, keeping subsurface reservoirs liquid even when the surface freezes. Second, extremophile ecosystems could cluster around geothermal hotspots, like those in Earth's Arctic hydrothermal vents, where chemistry replaces sunlight as the engine of life. But these scenarios demand a perfect storm of geology and atmospheric resilience that may simply not exist. Kepler 443b stands as a lesson in cosmic nuance. Not every planet in the habitable zone is truly habitable, and not every orbit fosters stability. Sometimes the universe offers not a cradle for life, but a test of its limits, a place where survival would mean rewriting the rules of biology itself. Just 17 light-years from Earth, close enough that you could spot its faint red sun through a backyard telescope, GJ3323b spins in quiet contemplation, a super-Earth caught between fire and ice. This rocky giant, 3 times heavier than our home planet, orbits so close to its dim red dwarf that its year flashes by in just over 40 Earth days. But don't let the tight orbit fool you. This star is so feeble that GJ3323b basks in only 35% of the sunlight Earth receives, placing it squarely in the habitable zone's chilly outer edges. What unfolds here isn't just a story of orbital mechanics, but a radical reimagining of how life might adapt to perpetual twilight. Unlike the violent flares of Proxima Centauri or TRAPPIST-1, GJ3323 star is a study in restraint, a red dwarf so calm it barely flickers. That stability could be the planet's greatest gift, While young red dwarfs typically blast their planets with sterilizing radiation during early eons, this older star has settled into a quieter middle age, offering JJ3323b a rare chance to hold onto an atmosphere. Models suggest its extra mass might have anchored a thick carbon dioxide blanket, a natural greenhouse cloak trapping just enough heat to keep water liquid despite the weak starlight. Picture a world where the air hums with pressure, where dense fog clings to valleys, and where the sun, a swollen crimson orb, never quite rises high enough to burn off the haze. The real marvel lies in the light itself. Earth's plants evolved under a golden sun, but JJ3323b's star bathes its surface in infrared-rich gloom like perpetual sunset. Photosynthesis here wouldn't rely on the vibrant greens we know. Instead, alien vegetation might develop pigments tuned to absorb those dim red wavelengths. Imagine forests of deep violet or inky black, their leaves straining to catch every scarce photon. Some scientists speculate organisms could even harvest heat directly, converting infrared energy into chemical reactions the way geothermal microbes do near Earth's volcanic vents. Tidal locking adds another layer of complexity. Like most red dwarf planets, one side likely faces eternal day, the other endless night. But JJ3323b's thicker atmosphere could work magic, ferrying warmth from dayside to nightside through planet-spanning storms. The Terminator line, where light and dark meet, might host a narrow Eden, where temperatures hover near freezing but don't plummet into lethality. Here, hypothetical organisms could exploit the gradient, thriving in the tension between warmth and cold. The James Webb Space Telescope could soon unravel these mysteries by hunting for water vapor or methane in JJ3323b's air. But even without confirmation, this world challenges our biases. It proves that habitable doesn't always mean Earth-like. Sometimes it means something far stranger, where life dances to the rhythm of a dim red sun. Captain B isn't just another exoplanet, it's a cosmic relic, a world so ancient it might have formed just 2 billion years after the Big Bang. Orbiting a dim red dwarf 12.8 light-years away, this super-Earth is older than our solar system itself, a survivor of galactic upheavals that flung it and its star from a long-dead dwarf galaxy into the Milky Way. But what makes Captain B so controversial isn't just its age, it's the fierce debate over whether this primordial planet could still harbor life despite its turbulent past. Discovered in 2014, Captain B initially made headlines as one of the oldest potentially habitable worlds ever found. At 5 times Earth's mass and orbiting its star every 48 days, it sits on the inner edge of the habitable zone, close enough that with a thick atmosphere, temperatures could allow liquid water. But here's where the arguments ignite. Captain's star is a subdwarf, a faint metal-poor remnant of that ancient cannibalized galaxy, and it burns with barely a fraction of our sun's energy. The planet would need an exceptional greenhouse effect to stay warm, yet its star's violent youth likely stripped away any early atmosphere. Picture a world that spent its first eons bombarded by radiation, its air scoured away by stellar winds, leaving behind a barren rock, or did it? Some models suggest a tantalizing alternative. If Captain B formed with a massive hydrogen envelope common for early universe planets, it might have clung to enough gas to rebuild an atmosphere over time. Volcanic outgassing or comet impacts could have replenished lighter molecules, creating a secondary blanket of air. The planet's strong gravity would help, trapping gases that weaker worlds would lose. Imagine a shrouded globe where the sky glows dim red, its dense air redistributing meager starlight to temperate pockets. Life here, if it exists, would be ancient beyond comprehension, organisms that evolved under conditions unimaginable on Earth, their biochemistry forged in a younger, harsher universe. Yet skepticism abounds. Critics point to the star's erratic rotation, evidence of past flares that could have sterilized the planet repeatedly. Without a magnetic field to deflect radiation, even a thick atmosphere might not shield the surface. Then there's tidal locking, the near certainty that one hemisphere bakes under eternal daylight while the other freezes in darkness. Optimists counter that tidal heating from the star's gravity could sustain subsurface oceans, offering refuge in the abyss where life might persist unseen. The most compelling clue lies in K2-18b's composition. Its star's low metallicity suggests the planet formed from primordial materials, lacking the heavy elements abundant in younger worlds. If life did emerge here, it might rely on exotic chemistry, perhaps silicon-based or thriving in ammonia-rich solvents, making it unrecognizable by earthly standards. Future telescopes could settle the debate by hunting for atmospheric traces, but even a null result would be profound. K2-18b forces us to confront a radical idea, that habitability isn't just about stable stars and gentle orbits, but about resilience, about worlds that endure the universe's chaos and still whisper, against all odds, the possibility of life. K2-18b drifts through the cosmos like a puzzle box waiting to be opened, a world that by all accounts should be a prime candidate for life, yet hides complexities beneath its promising resume. Located 1,700 light-years away in the constellation Lyra, this exoplanet orbits squarely within its star's habitable zone, a region where liquid water could theoretically pool on its surface. But habitable zone is a deceptively simple term. The reality here is a delicate dance between opportunity and obstacle, where the planet's potential hinges on weathering the tantrums of its unpredictable host. K2-18b's star is a K-type dwarf, smaller and cooler than our Sun, but far from docile. While these stars are generally more stable than their flaring red dwarf cousins, they still undergo phases of intense magnetic activity, especially in their youth. The planet likely endured eons of harsh ultraviolet radiation and violent stellar winds during its star's early years, events that could have stripped away any primordial atmosphere or boiled off surface water. Picture a world that started as a potential paradise, only to be scoured by cosmic storms, its fate hanging on whether it could cling to the volatile ingredients of life. Yet resilience might be K2-18b's hidden strength. At roughly twice Earth's size, its stronger gravity could have helped it retain or rebuild an atmosphere over time. Volcanic activity might have replenished gases, while impacts from icy comets could have delivered fresh water to its surface. The planet's orbit, just 38 Earth days, places it close enough to its star that tidal forces could flex its interior, generating geothermal heat to sustain subsurface oceans even if the surface became barren. Imagine a world where life retreated underground, thriving in hydrothermal networks shielded from the chaos above, much like Earth's extremophiles near volcanic vents. The star's current calm is another wild card. Having aged out of its most turbulent phase, it now offers K2-18b a rare window of stability. Without constant radiation blasts, the planet might have developed a protective ozone layer, or fostered photosynthetic organisms adapted to its star's dimmer, redder light. But tranquility comes with its own challenges. A quieter star means less energy overall, forcing any potential ecosystems to operate on a leaner budget. Plants here wouldn't bask in golden sunlight, they'd strain to harvest every scrap of infrared, perhaps evolving jet-black pigments to absorb every available photon. The most tantalizing unknown is water. K2-18b's density suggests a rocky composition, but whether it holds oceans, ice caps, or just traces of moisture depends on atmospheric chemistry we can't yet measure. Future telescopes might detect water vapor or oxygen in its air, but even those signals could be deceptive. Oxygen can arise from non-biological processes, and water might survive only in transient states. The planet could be a cautionary tale, a reminder that habitable zone is just the first question in a much longer test. K2-18b doesn't just challenge our assumptions about where life can thrive, it forces us to confront the endurance required to survive the universe's rough drafts. Not all habitable zone planets are created equal, and sometimes the most promising worlds are those that have fought the hardest to stay that way. Lytton Star B spins through the cosmic dark just 12 light-years from Earth, so close that its star is visible through amateur telescopes. This unassuming super-Earth, 3 times heavier than our own world, orbits a red dwarf so tranquil it barely flickers, making it one of the most promising havens for life we've ever found. Unlike the violent tantrums of Proxima Centauri or TRAPPIST-1, Lytton's star emits almost no flares, offering its planetary companion a rare gift in the red dwarf realm: stability. Picture a world where the sky isn't periodically scorched by radiation, where an atmosphere could persist for eons, and where the chemistry of life might unfold uninterrupted beneath a steady crimson sun. What makes this planet stand out isn't just its serene star, it's the way its mass and orbit conspire to create ideal conditions. At 1.4 times Earth's radius but packing 3 times the heft, Lytton Star B has gravity strong enough to cling to a thick atmosphere, yet not so crushing that it would smother geological activity. Its 28-day year places it squarely in the habitable zone, where temperatures could allow liquid water without boiling it away or freezing it solid. But here's the twist: this world is likely tidally locked, with one face forever bathed in dim starlight and the other shrouded in eternal night. That's where atmospheric dynamics become the hero of the story. Climate models suggest that with even a moderately thick carbon dioxide blanket, winds could ferry warmth from the dayside to the nightside, preventing the entire planet from becoming a frozen wasteland. Imagine cyclones the size of continents acting as planetary couriers, redistributing heat along the twilight border where temperatures might hover in a life-friendly range. The dayside could host sprawling, shallow seas warmed by the star's perpetual glow, while the nightside's deep freeze might be punctuated by geothermal oases, volcanic hotspots where subterranean heat keeps pockets of water liquid against all odds. The star's quiet nature adds another layer of potential. Most red dwarfs spend their youth blasting planets with ultraviolet radiation, but Lytton's star is an elder, its turbulent phases long past. This means any primordial atmosphere, assuming it survived the early chaos, might have evolved into something breathable over billions of years. Nitrogen could dominate, as on Earth, with traces of oxygen or methane hinting at biological activity. Or the air might be a dense mix of carbon dioxide and water vapor, creating a global greenhouse that compensates for the star's faintness. The ultimate clue lies in the planet's reflectivity. If Lytton Star B has oceans, they'd appear as dark patches in telescope observations, absorbing starlight, while ice caps would shine brightly. Future instruments might even detect the glint of sunlight off liquid surfaces, a telltale sign that this world isn't just habitable in theory, but inhabited in fact. Until then, Lytton Star B lingers as a quiet enigma, a nearby neighbor with all the right ingredients for life, orbiting a star that's been keeping the cosmic peace for longer than our solar system has existed. Kepler 638b doesn't just orbit its star, it glides through the cosmic equivalent of a slow dance, completing a leisurely year once every 259 Earth days. This Earth-sized world, nestled 1,600 light-years away in the constellation Cygnus, takes its time circling a sun-like star, a rhythm that could create something rare among exoplanets' seasons. Not the fleeting, chaotic shifts of tidally locked worlds, but predictable, cyclical changes akin to our own spring, summer, fall, and winter. Picture a planet where the tilt of its axis, like Earth's 23.5 degrees, might angle its hemispheres alternately toward and away from starlight, painting its landscapes with the brushstrokes of time. What makes this possibility so tantalizing is the star itself. Kepler 638 is a G-type star, nearly identical to our Sun in temperature and size, but slightly older and calmer. This similarity means the planet receives sunlight in familiar golden hues, with intensity varying as it travels along its oval-shaped orbit. Earth's seasons arise from axial tilt, but here, the combination of tilt and orbital eccentricity could amplify climatic shifts. Imagine summers where the planet's closer approach to its star bakes continents under intense heat, followed by winters where the distant retreat brings months of cooling rains or frosts. These cycles wouldn't just affect temperature, they could dictate migratory patterns for hypothetical life forms, drive ocean currents, or even influence atmospheric chemistry, with gases condensing and vaporizing in rhythmic waves. The planet's size adds another layer of intrigue. At just 1.2 times Earth's radius, its gravity would feel reassuringly familiar, potentially allowing for similar geological processes like plate tectonics. Active tectonics could regulate carbon dioxide levels over millennia, stabilizing the climate against the extremes of its elongated orbit. Volcanic outgassing might replenish atmospheres stripped by stellar winds, while mountain ranges born from tectonic clashes could disrupt weather systems, creating microclimates where life could shelter. Yet mysteries loom. Kepler-638b's orbit isn't just long, it's slightly eccentric, tracing an ellipse rather than a perfect circle. That irregularity might push the limits of habitability. During its closest stellar approach, the planet could suffer scorching droughts, while at its farthest point, ice might creep across its oceans. The question isn't just whether water exists here, but whether it can persist through these pendulum swings. Some models suggest that a thick atmosphere could buffer these extremes, redistributing heat like a planetary thermostat. Alternatively, life might adapt to the rhythm, flourishing in brief golden intervals between climatic extremes, like desert blooms after rare rains. The James Webb Space Telescope could soon unveil clues, analyzing atmospheric gases during different orbital phases. A spike in water vapor during summer or a buildup of carbon dioxide in winter would reveal a world breathing with the seasons. For now, Kepler-638b stands as a cosmic lesson in balance, a reminder that habitability isn't just about location, but about how a planet moves through time and space, weaving its own tapestry of light and shadow. Wolf 1069b spins through the cosmic dark just 31 light-years from Earth, a silent neighbor that might be harboring one of the most Earth-like environments we've ever found outside our solar system. Discovered in 2023, this unassuming world barely tips the scales at 1.26 times Earth's mass, making it one of the lightest exoplanets ever detected in its star's habitable zone. But what truly sets it apart isn't just its size, it's the delicate thermal balancing act unfolding under its dim red sun. At first glance, the numbers seem almost too perfect. Wolf 1069b's equilibrium temperature, the theoretical average if it had no atmosphere, hovers around -9.4 degrees Fahrenheit. That's colder than a Siberian winter, but here's the catch. Equilibrium temperatures ignore atmospheric magic. A modest greenhouse effect, something as simple as an Earth-like mix of nitrogen and carbon dioxide, could bump surface temperatures into the liquid water range. Picture a world where the air itself acts like a thermal blanket, redistributing just enough warmth to let ice melt into rivers and seas. The planet's orbit, a snug 15.5 Earth days, places it far enough from its star to avoid tidal locking's extremes, meaning it might even rotate, offering day-night cycles akin to home. Then there's the star itself, Wolf 1069, a red dwarf so tranquil it barely flickers. Unlike Proxima Centauri's tantrums or TRAPPIST-1's flares, this star emits minimal ultraviolet radiation, giving any atmosphere a fighting chance to persist. Stability is this system's secret weapon. Red dwarfs burn for trillions of years, meaning Wolf 1069b could have enjoyed the same gentle conditions for far longer than Earth has existed. Life here, if it exists, might have had double or triple the time to evolve, crafting ecosystems in slow motion beneath a sun that barely ages. yet mysteries linger beneath the optimism. That Earth-like mass suggests a rocky composition, but we've yet to confirm an atmosphere. If stripped away long ago, the planet could be a frozen tomb, its potential locked in ice. Alternatively, volcanic activity or comet impacts might have replenished gases, creating a secondary atmosphere rich in life-friendly chemistry. Future telescopes could settle the debate by hunting for the faint fingerprints of water vapor or methane in its air, telltale signs that this world isn't just habitable in theory, but a living, breathing sibling to Earth. Wolf 1069b quietly challenges our assumptions. It's not the closest potentially habitable world, nor the most dramatic, but in its unremarkable stillness lies a revelation that the universe might be littered with Earth-mass planets where conditions are just stable enough, just long enough for life to whisper into existence. And sometimes it's the quiet ones that speak loudest. HIP 67522b shouldn't exist, at least not where we found it. This searing giant, over 10 times Jupiter's mass, orbits a newborn star so closely that its year flashes by in just 7 Earth days. Planets like this hot Jupiter's typically broil in stellar embrace, their surfaces scorched beyond recognition. Yet HIP 67522b defies expectations by lingering at the very edge of its star's habitable zone, a cosmic paradox that rewrites the rules of planetary formation. What makes this world so baffling starts with its age. At just 17 million years old, a cosmic infant compared to Earth's 4.5 billion years, its existence challenges everything we know about how gas giants form. Conventional wisdom says planets this massive need time to coalesce from swirling disks of gas and dust, yet here's HIP 67522b, fully formed before its star has even settled into maturity. The sheer speed of its birth suggests alternative pathways, perhaps gravitational instabilities that collapsed vast swaths of protoplanetary material in a single, violent gasp. But the real puzzle is its precarious perch in the habitable zone. While its dayside roasts at thousands of degrees, tidal forces might stretch and flex its atmosphere, generating enough heat to maintain temperate pockets on the night side or in upper cloud layers. Imagine a world where the Terminator line the boundary between eternal day and night, hosts swirling storms of water vapor and ammonia, their chemistry churning in perpetual twilight. Some models even propose that such a planet could retain moons, their surfaces warmed by reflected heat from the gas giant's glowing atmosphere. These moons, not the planet itself, might offer refuge for liquid water, a cosmic loophole for habitability in the unlikeliest of places. The star adds another layer of intrigue. HIP 67522 is a rapidly rotating G-type star, unleashing torrents of ultraviolet radiation that should have evaporated any nearby protoplanetary disk before giants could form. Yet here's its massive companion, stubbornly orbiting just far enough to avoid spiraling into destruction. One theory suggests the planet migrated inward after forming farther out, its path altered by interactions with leftover disk material or unseen sibling planets. Alternatively, it might have formed right where it is, a scenario that would force us to rethink how quickly planetary cores can nucleate in turbulent young systems. The implications ripple outward. If HIP 67522b can exist here, how many other hot Jupiters have we misjudged? Could their moons hidden from our telescopes harbor subsurface oceans or even life? Future instruments might detect atmospheric compositions or thermal gradients hinting at these possibilities. For now, this tempestuous adolescent planet stands as a reminder that the universe's rulebook is far from complete, and sometimes the most unlikely worlds hold the keys to rewriting it. TOI-1452b doesn't just orbit its star, it shimmers with secrets beneath an alien sky. 100 light-years away in the constellation Draco, this enigmatic super-Earth has astronomers buzzing for one electrifying reason: it might not have a surface at all. Instead, this world could be cloaked in a globe-spanning ocean so deep it makes Earth's seas look like puddles. Imagine a place where water isn't confined to basins but stretches endlessly, pressing down under layers so dense they transform into exotic forms of ice hotter than lava. What makes this planet so extraordinary starts with the numbers. TOI-1452b is 70% larger than Earth but nearly 5 times as massive, a density that screams water world. For context, Earth's water makes up less than 1% of its mass, while this planet's composition suggests a staggering 30% could be liquid or ice. That's the equivalent of dumping every ocean on Earth into a blender, then multiplying it by a factor of hundreds. But here's where the strangeness deepens. At these extreme pressures, water doesn't behave like anything we know. Miles below the surface, where the weight of the ocean crushes molecules into submission, water might solidify into hot, black ice forms like ice 7 or superionic ice that conduct electricity and flow like molten metal. The star this planet circles adds another layer of intrigue. TOI-1452 is a quiet red dwarf in a binary system, meaning the planet basks under 2 dim suns instead of 1. Its 47-day orbit places it snugly in the habitable zone, but the real heat might come from within. Tidal forces from its star could be flexing the planet's core, generating enough geothermal energy to keep subsurface layers liquid even if the surface freezes solid. Picture hydrothermal vents in the abyss, not made of rock but of glowing, pressurized ice, their chemistry bubbling with possibilities for life. Then there's the atmosphere question. Most water worlds struggle to retain substantial air under the weight of their own oceans, but TOI-1452b's gravity might cling to a thick steam envelope. This vapor blanket could act like a planetary pressure cooker, trapping heat and preventing the entire ocean from freezing into a solid block. Observations hint at traces of water vapor in its air, but confirming this requires more precise measurements, ones the James Webb Space Telescope could soon deliver. The ultimate mystery, whether life could exist in such a place. Earth's extremophiles thrive near deep sea vents without sunlight, but TOI-1452b's hypothetical organisms would face pressures unimaginable on our world. Their biochemistry might rely on solvents other than water, or exploit the conductive properties of exotic ices to harvest energy. Some scientists speculate that tidal heating could create habitable pockets where liquids and solids mix, forming a slurry ripe for complex chemistry. TOI-1452b isn't just another exoplanet, it's a challenge to our very definition of Earth-like. It proves that habitability isn't just about rocky shores and golden sunlight. Sometimes the most promising worlds are the ones drowning in possibility. From scorching super-Earths to frozen ocean worlds, these 30 exoplanets prove the universe writes its rules in starlight and chemistry far beyond our earthly imagination. Each one challenges what we thought we knew about life's possibilities. Planets where photosynthesis happens under crimson suns, where tides are pulled by sibling worlds instead of moons, and where entire biospheres might thrive in perpetual twilight. Some orbit calm stars that have burned steadily for billions of years. Others dance with stellar tempests, clinging to habitability through sheer planetary resilience. What unites them isn't similarity, but diversity, a cosmic menagerie proving that life, if it's out there, could wear infinitely more faces than we've dared to dream. The search is just beginning. Telescopes like James Webb are already peeling back the atmospheric veils of these distant worlds, hunting for the faint chemical fingerprints of oxygen, methane, or other biosignatures. Future missions, the Habitable Worlds Observatory, Europa Clipper, even ambitious starshade projects that could block stellar glare to reveal Earth-like planets will push our vision further. Imagine decoding the light from an exoplanet's atmosphere and finding not just gases, but the industrial pollutants of a civilization, or the shimmer of artificial megastructures harnessing their star's energy. The answers may come not in generations, but in our lifetimes. But here's the most thrilling truth: you're part of this story. Every time you look up at the night sky, you're witnessing the same stars that might shine down on alien oceans. Every question you ask about these worlds, how they form, if they harbor life, whether we'll ever hear their whispers, fuels the collective curiosity driving science forward. So keep wondering. Click that subscribe button to join us as we unravel these cosmic mysteries together. Drop your wildest theories in the comments. Could Proxima be host silicon-based life? Might K2-18b's Haitian oceans be fizzing with unknown biochemistry? The universe isn't just stranger than we imagine, it's stranger than we can imagine. And the next chapter, it's ours to write.